In this course, our main focus is CMOS integrated circuit, their IC layout design. Silicon in the periodic table is located in column 4A, which is a basic material for CMOS IC, and that is called a substrate for our particular purpose. The atom nucleus has 14 proton, and the first energy level has 2 electrons, right, represented here in blue. And there are 8 electrons in the second energy level, and only 4 electrons in the third level. The 4 electrons in the third energy level are called valence electron, which is shared with other electron atom. Let us use, here is the single silicon atom by itself. This is the silicon. The 4 radial line represents valence electron to be shared with other atoms. So since there are 4 are missing, so 4 of them are drawn, and they repel each other, forming an angle between radial line of 109.5 degree arc. The silicon atom has 4 links, as we can see, and the link is connected to other atoms. Typically, there are 6 atoms. So here we have, like this atom, one valence is shared with this, that one is shared with this. So eventually, the remaining 3 of this leftmost atom is also to be linked to another 3 more atoms. So that is the basic atom arrangement based on the 6 atom pattern. They extend indefinitely, so they create a lattice, shown here. The chain of 6 atom pattern create this silicon lattice. The lack of electron is called a hole. This is why silicon is not an insulator, because of that diffusion, because of the hole. But it's not a good conductor either. So it is called a semiconductor due to its electrical property. And the number of electrons which participate to the conduction is called intrinsic carrier. And the concentration of the intrinsic carrier is known numerically, which I will not mention. Shikar textbook has the specific of that. When the temperature increases, the intrinsic carrier density also increases. So the concentration of free electron is assumed to be equal to the concentration of the free holes. To increase the conductivity of an electron, material like so-called dopant are introduced into the silicon lattice. But to add more electron into the lattice artificially, like phosphorus or arsenic atom, are inserted in a small proportion to the silicon crystal. Since there are 4 valence electrons, find room in the lattice, 1 electron is released and participate in electrical conduction. Consequently, phosphorus and arsenics are named electron donors with an N-type symbol, so N-type semiconductor. A very high concentration of this is donor is called N++. A high concentration of donor is coded as N+. Very high is plus plus. High is N+. A low concentration of donors is called N-. Boron and phosphorus and arsenics are used as acceptors and donors of electron to change the electrical property which affect the semiconductor conductivity. So a missing valence electron creates a hole, and a dopant boron atom is usually inserted in the lattice to fill the hole. And typically a pip valence electron of the phosphorus released in the lattice, and the phosphorus atom is inserted when the phosphorus atom is inserted into the lattice. So the boron added to the lattice create a hole, which is called a p-type, while phosphorus create a free electron, so-called n-type. Now, silicon dioxide is a natural and the most convenient insulator used to create IC. And it is somewhat like this, where the atoms, silicon atoms, links through the oxygen, which is shown here in red, to the neighboring atoms. Silicon lattice boron is like this, while the silicon lattice phosphorus, a brief bird's eye view of the silicon material used for CMOS IC design.